But it turns out now that the general view is that black holes do not erase information from the universe.
For decades, physicists believed that once something crossed the event horizon of a black hole, it was lost to the universe forever, along with any information it carried. But new data is challenging that assumption. The James Webb Space Telescope, JWST, has captured something around ton 618, one of the most massive black holes ever discovered that defies everything we thought we knew about black hole behavior. Located over 10 billion light-years from Earth, ton 618 is a cosmic giant, over 66 billion times the mass of our Sun. This hypermassive black hole is so far away that observing it is like peering back in time, to a universe that was still in its infancy. Until now, ton 618 appeared to astronomers as little more than a distant point of light. But JWST's powerful infrared instruments have revealed something startling: rhythmic, violent bursts of energy pulsing from the edge of its event horizon, energy patterns that simply shouldn't exist. These aren't random emissions from superheated matter falling into a black hole. They're structured, rhythmic, and they're emerging from a region where, according to Einstein's general relativity, nothing, not even light, should be able to escape. So, what's really happening at the edge of this cosmic behemoth? A black hole. Unlike any other astronomers expected ton 618's infrared signature to resemble that of other supermassive black holes. A relatively uniform glow from the accretion disk, the disk of matter spiraling toward the event horizon. Instead, what JWST detected were intense pulses of infrared radiation occurring at regular 67-minute intervals. More shockingly, these pulses formed distinct geometric patterns, almost like energy was moving through invisible structures around the black hole's perimeter. Infrared instruments aboard JWST, specifically MIRI, Mid-Infrared Instrument, and NIR SPEC, Near-Infrared Spectrograph, picked up these emissions with an unprecedented level of detail. Cooled to just above absolute zero, these instruments allowed JWST to detect even the faintest heat signatures from deep space without interference. Dr. Jane Rigby, Operations Project Scientist for JWST, explains, Webb's infrared capabilities are revealing black hole behavior we simply couldn't observe before. These findings are forcing us to question some of our most fundamental assumptions about how matter and energy interact in extreme gravitational environments. Rhythmic bursts from the void. The energy signatures observed weren't just intense, they were shockingly organized. Bursts of radiation pulsed like clockwork from multiple points around ton 618's event horizon. This precise regularity suggests something more than chaotic gravitational forces at work. It implies a mechanism, something structured, potentially even guided. This challenges the very foundation of black hole physics. The event horizon is supposed to be a one-way boundary. It's the point of no return. Yet, JWST's data appears to show not just matter being consumed, but energy escaping, repeating, pulsing, as if trying to signal something deeper. Theoretical earthquake. The discovery has sent shockwaves through the scientific community. While more data is needed, researchers are already proposing several radical theories to explain what JWST saw. 1. Interaction with dark energy. Some astronomers suggest the energy bursts could be evidence of matter interacting with dark energy, an invisible force thought to be responsible for the accelerated expansion of the universe. If ton 618 is large enough to trigger such interactions at its event horizon, it might explain these unusual emissions. 2. Extreme accretion disk physics. At 66 billion solar masses, ton 618's accretion disk might behave unlike anything we've seen before. Massive shock waves, magnetic reconnections, or even turbulence on an interstellar scale could be causing these structured patterns in the infrared spectrum. 3. Spacetime distortions and gravity echoes. Some theoretical physicists believe the rhythmic pulses may be evidence of gravity echoes, ripples in spacetime caused by quantum effects that are amplified in environments this extreme. These echoes could be visible only around black holes of such incomprehensible size. 4. Hawking radiation at a new scale. Could we be seeing Hawking radiation, the long-theorized emission of particles from black holes, for the first time, TON 618's massive scale might amplify quantum processes at the event horizon enough for them to become observable, providing a glimpse into the mysterious frontier between gravity and quantum mechanics. 5. Frame dragging effects. Another possibility is that the infrared pulses are the result of frame dragging. As TON 618 spins, it may be twisting space-time around it so violently that the distortion becomes visible as structured patterns, vortices of warped reality. A global scientific effort. The implications of this discovery are enormous. Multiple observatories around the world are now coordinating to study TON 618 in every spectrum of light. NASA's Chandra X-ray Observatory, the Very Large Array in New Mexico, and the upcoming Extremely Large Telescope in Chile are all joining the investigation. Even the Event Horizon Telescope, EHT, famous for capturing the first image of a black hole, is reconfiguring its global network to target TON 618. This multi-wavelength approach could confirm whether the strange infrared emissions are linked to known phenomena or reveal something entirely new. A special conference at the Max Planck Institute has already been organized to review the findings. While many scientists urge caution, no one is denying the magnitude of what's been observed. As Professor Brian Cox put it, what we're seeing challenges our entire model of black holes. TON 618 isn't just enormous. It's behaving in ways that weren't supposed to be possible. It's like finding a skyscraper in a village of huts. It doesn't just stand out, it rewrites the history of architecture. Cosmic dawn and the evolution of giants. TON 618's mass alone is a mystery. How did such a massive black hole form when the universe was still so young? This raises new questions about the early universe and the evolution of cosmic structures. Did supermassive black holes form faster than we thought? Or did they follow an entirely different process we've yet to understand? If the strange energy patterns are linked to TON 618's rapid formation, they might hold clues about how the universe's first galactic cores emerged from the primordial chaos following the Big Bang. Some theorists also believe the energy pulses could help solve the information paradox, the unresolved question of whether data that falls into a black hole is lost forever, or somehow preserved. These emissions might be a form of quantum encoding at the edge of spacetime, suggesting that event horizons are far more complex than previously believed. What's next? The Laser Interferometer Space Antenna, LISA, scheduled to launch in the 2030s, will be capable of detecting gravitational waves from black holes like TON 618. If it detects ripples that match what JWST is seeing, it could confirm the existence of space-time echoes, quantum radiation, or something else entirely. According to Nobel Prize-winning physicist Dr. Kip Thorne, JWST's observations of TON 618 might be the most significant discovery in black hole physics since gravitational waves. If verified, they'll fundamentally change how we understand event horizons and the nature of space-time. Still, definitive answers will take time. Scientists expect initial cross-observatory data within a year. Complete theoretical models may take far longer, potentially requiring breakthroughs in quantum gravity theory itself. A new chapter in cosmic science, TON 618, is no longer just a distant curiosity. It's now the center of one of the biggest puzzles in astrophysics. Structured energy emissions at the edge of a black hole challenge our models of gravity, quantum mechanics, and even the origin of the universe. The cosmos has once again reminded us that it holds secrets far beyond our current understanding. As we point our most powerful instruments toward the stars, we don't just see the past, we glimpse the deeper laws that govern reality itself. If you're fascinated by discoveries like this, hit the subscribe button and turn on notifications. We bring you the most intriguing space phenomena every week. What do you think is happening at the edge of TON 618? Could it be quantum radiation, dark energy, or something even stranger?